Thank you.
Okay, I have that on now. Thank you.
Okay, now I'll straighten out the view.
Just to give you an idea, so when I did high energy physics, I was studying, I thought that was like the way you study the universe. It was kind of like you were trying to go backwards in time, early Big Bang stuff. And what we were doing was then called the Tevatron. It was the highest energy accelerator in the world. And it was ran at 1 tera electron volt, very, very high energies, very short distances. By comparison, the LHC is running 14 tera electron volts currently. So I thought these are the secrets to the world. And now when I kind of did this whole thing, I got involved in quantum key distribution, which I'll talk a little bit about that. Is how do you press quantum information on a single photon? I use photons all the time. And then from there, I got involved in quantum computing, and I've been doing that for about 20 years. But the fun part is that when I give physics talks, I will say I went from tera electron volts to micro electron volts. There's 9 orders of magnitude difference. And to give an idea, what is an electron volt? It's a unit of measure of energy. And if I take an object like this, and let's just assume that it weighs like a kilogram, and I lift it by about that distance, that's about an electron volt amount of energy, roughly speaking. So that's not much energy. So having said all that, that's kind of briefly what I'm talking about. And right now I am working for IBM Research in Yorktown Heights, New York. Hope to come back here one day, and that's why I'm kind of here, is I'm trying to build up my social environment again and local people. And I deploy quantum computers around the world, and I will show you now. I'm going to my screen.
Again, I'm going to shut my, I think I'm sharing, so I'm going to stop my sharing if that's what I'm doing.
It's working.
So let me start there. So this is like the tip end, what we call the chandelier. And it's a mock-up of what's inside the cryostat, and I'll get into that in a few moments. But it's kind of a work of art that is all gold-plated, and all those little wires there, they're coaxial cables. I'm going to talk about the fact that we make artificial atoms here, and we actually impress information on those artificial atoms. I'm going to constantly be talking about like what's the connection between radio and that. This is all run at 5 gigahertz. So that's like your Wi-Fi. And part of that is that you can get RF equipment in that frequency fairly inexpensively. So this is, I'm going to spend a couple of moments here. This is the system that I deployed in Germany. Now, you and I were talking just before the meeting, and you said you're an industrial artist. So one of the things that's really cool, okay, so I'm a physics guy. We like, how do we make it work? How do we build it? And then there's a whole bunch of industrial artists I work with, and like, yeah, you know, if you're going to press this out in the real world, you can't just do that because you're geeking out on it. You love it. It's wonderful. You got to make it sure that other people can interact with it. So believe it or not, this was actually modeled after the monolith from 2001. So it kind of hit it. And it's kind of fun. But as you walk through this, what I would suggest you do, and I really do like to be interrupted. I think it's more important that you interact with it. You'll remember the conversation better. You should ask questions. You should ask me hard questions. Some of them I won't be able to answer. But then the other part of this is, how do you connect with this? Like you could say, well, but I'm a mechanical engineer. How does that connect to this? Or, you know, you're an industrial artist. Well, I'm just showing you the cross section of how industrial artists fits into this whole scheme of things. No matter what you touch, I'm talking about a new technology that we're trying to bring into the world. I think this is going to change things in the same way that bipolar and CMOS did for computers. This is going to bring us a new industry that will kind of breathe a new engineering life into the United States and around the world for the next 60 years or so.
You're going to show us the back?
I will. So,
Back's more fun.
you know, let's go back in history. It's like, and I'll only spend 2 slides on this. You know, how did this come about? I mean, there's the quantum revolution that happened in 1920, which was, you know, a lot of people that you hear names of, Dirac and Pauli and all these German physicists coming up with these great ideas. And Heisenberg, you know, the Heisenberg uncertainty principle, they all came up with quantum, and they were trying to explain some weird physics phenomena they didn't quite understand. But how does that really relate to computing? So there's this guy, Ralph Landauer, who was involved in IBM research back in the late 50s. And at that time, IBM was working on ostensibly vacuum tubes. They were thinking about moving over to transistors, but they hadn't yet. And somebody posed the question, what is the minimum amount of energy required to compute? Now, that's a really weird kind of question. Like, okay, you think of a computation, you write something down on a sheet of paper and you're adding numbers. There's a amount of energy associated with that. That's really a weird concept. So it got people thinking, and that's the relationship he's saying that energy is the Boltzmann constant times the temperature and the actual log of two. A lot of math there. If you want to talk more deeply, I'll go into that later. But it really was the start of something where people started to really think and say, gee, that's a really interesting question. Where does that lead? Because there is an awful lot of energy spent on compute. If you look at compute centers around the world right now,
Iceland?
well, they were talking about Iceland just because the energy is cheap and the cooling is cheap.
Just leave the door
You
open.
just leave the door literally. I mean, literally, you. And what happens also is that you point out something that's really important. Is okay? Suppose you've got, and this is not unusual. You say you've got 50 megawatts of compute power or 100 megawatts. That's a lot of energy. 90% of that energy gets released out as heat. That's a huge waste. So that it comes forward. We're going to go to 1981. And I've skipped a whole bunch of stuff, but there were a whole bunch of intermediate people, and they were talking about these things called reversible logic. What would happen if, okay, there's this second law of thermodynamics that says I can push energy forward, but if it can be adiabatic, which means it can go backwards, and there's no energy. And they were talking about how much work is done, and that sort of thing. They're asking all sorts of very strange questions. And at this conference they held at MIT, Charlie Bennett, who was a guy that I worked with at IBM Research, went up to Richard Feynman, a physics name that probably everybody's heard of, and said, what would happen if we actually tried to compute with an atom or a photon or something like that? Now, like on an atom, you've got different energy levels, electron levels, that sort of thing. And Feynman was like, that's a really interesting idea. And a year later, he produces a paper on that. I was lucky enough, I was in grad school when he produced his paper, and he came and talked to us graduate students. It was kind of interesting. He's talking to us, he's telling me all about it. His big thing is, quantum mechanics is really difficult to model, so this would be a great way to model it. I'm like, yeah, okay, I'm going to do my energy physics. This is all bullshit. But here I am, 30 years later, after grad school, and I'm actually doing what he said. But it's an interesting kind of chain of events. So fast forward, we're here today, and it is really remarkable. I kind of skipped a lot of history here. I'm really going to be mindful of time. But there's a whole bunch of things that got demonstrated along the way. There are events like there's a thing called Shor's algorithm that threatens to break RSA keys, that the government started getting really interested in that. That's going to be a real problem. There was, you're in computer security, so you understand what I'm talking about there. People freaked out in 1995 and said, oh crap, if that could happen, the United States better be the first one to do it. So the US government dumped a pantload of money into quantum computing. The first practical demonstration came about not too long after that, when they factored the number 15 in 2000. Which, I think seemed like a big deal, but at the time, actually computing numbers on solids was a pretty weird idea. So I'm going to fast forward now. I'm going to start talking specifically about the type of qubits that I work with. Now, what is a qubit? So on the left-hand side of this, you've got bits, and there's a schematic of a piece of CMOS that does that's a NAND gate there. And so when you encode information on transistors or in capacitors or anything like that, you're encoding the information. It's either a 0 or a 1. It's usually a voltage level. And you just say, you're going to switch it on or you're going to switch it off. It's highly serial. You may put a whole bunch of these in you've heard people say registers. I don't know if they get that low in computer science anymore. Usually people are talking Python or something like that. But if you go down to the assembly level, you're going to talk about registers. That's kind of like a whole parallel set of these bits together. You can do computations, but they're largely, that's how you represent large numbers, and then the operations are highly serial. So that's why the clock rate becomes really important. How fast can I do an addition? And honestly, Addition is about the only thing you really do on a computer. Everything else is derived from addition. Multiplication is just a lot of fast additions. Then we come to quantum computer, and there's kind of a way on this chart, you're saying there's some sort of analog, there's information in it, unit, which is bits in a classical sense, which is a 0 or 1. Qubits, which I'm going to show you, you can have actually anything in between. Demonstrate that in a minute. And transition switches, which are your physical device, and we're using this superconducting Josephson junction circuit, and I'm going to relate that back to radio in just a moment. And then NAND, well, you've got NANDs, GANs, ORs. If you went to electrical engineering college, the first thing I learned was
if you went to my general class, license class, you found out about that.
Well, but you could build an entire computer out of NAND gates. So that's kind of a weird concept. And we have those are called universal gates, and you kind of say, I'm going to put together a set of universal gates and build a whole computer out of that. So in both cases, we've got that. And ours is the C0, that's the powerhouse. Now I'm going to introduce to you to what is a quantum. And this, I'm going to ask you for feedback. What I really try to do is I really try to think very hard is how I've spent 30 years doing this. I've spent 30 years thinking about it. And so I have a certain way of thinking about it. I'm trying to figure out, how do I get that? How do I bring that to you in a way that you can absorb the information? So I'm going to hit you with a lot of really weird terms and concepts. I would really appreciate it if you could come back to me and say, oh, you're way over my head, or you're kind of on target, or, whatever. Just give me some feedback. I really appreciate it. So on here, I've got many, many, many things which talk about what is a qubit. So I'm talking about, so I've got a hydrogen atom, for instance, and I've got an electron that's circulating around a hydrogen atom. I can encode a bit of information on that hydrogen atom by exciting it. You can excite it into a higher order state. Now, like you guys have seen neon signs. Everybody's seen a neon sign. What that fundamentally doing is putting electrical charge through a gas. It could be neon, it could be on, depends on what color you want. And what you're doing is you're taking those electrons and you're actually kind of almost associating with them, and as they collapse, they emit photons. And those photons are a very specific color. And the color is, if I, in this particular notation I'm using on the left-hand side where I'm talking about energy, that's dropping down into the ground state. So I'm at a high excited state, I'm dropping down to the ground state. So when I talk about, I want to press a bit of information on a quantum state, it doesn't matter what my system is. I just say there's a ground state, the lowest energy state, and I choose some other state that I can address, and that's going to be my 1. And the energy in that, instead of being a continuum, like I would say standard, I guess CMOS today is like 3.3 volts, but back in my day it was 5 volts. And then there's those people who dealt with Echo, which was another weird one, where you did -2 to 5, I think, in order to get fast switching. But in here, what you're talking about is the energy between those two states is actually equal to H omega. And omega is the standard thing that you use in your radio, which is 2 pi times the frequency of the transition. And H is what's called Planck's constant. So if you guys have heard of this thing, what they call the Heisenberg uncertainty constant, it says that you can't actually measure anything below that Planck scale. And the Planck scale is actually, now I'm going to relate that back to the universe, that they always talk about the Planck scale as being birth of the universe. So now I'm going to really introduce you. I know Paul and I have talked about this over breakfast many times. I'm going to introduce complex numbers. Tell me, don't do that.
Complete number.
My favorite. So yeah, okay, you could say complete numbers. So there's this weird notation in physics, and these are called bra and cat, because the Heisenberg and those guys, they didn't know. Anybody ever done signal processing in here? So some people have done that. If you've ever done any sort of matrices or anything like that, linear algebra, there's a whole set of mathematical notation, and these guys they weren't tuned into that, so they invented it all over. They came up with their own set of notation. It's kind of stuck. So that's what they're saying here. And what I'm doing is what's called a linear superposition of both a 0 and a 1. I've got these numbers, the Greek letters, alpha and beta. Those can take on unusual values. Let's forget about complex numbers for a moment, but they can take on values. That means I can create a phase. So I can, not only am I, and I'm going to show graphically on the right-hand most side how a quantum bit is actually encoded. So I can think of a sphere. Now I'm going to stand up here and hopefully I'm with a view. Watch the camera. So let's say I'm at 0 with my arm, and I want to get to 1. So I do what's called a pi pulse. It's going to be a little funky. You're going to say, what's a pi pulse? I'm like, I'm going to do a pi, or a 180-degree rotation. I'm going to go to the bottom of the sphere, and that's a 1. So if I'm now going to use one of my superconducting qubits. I'm going to hit this with a 5 gigahertz signal on a specific system, which I'll talk to you about in a minute. And I'm going to go from a 0 to a 1 with that pulse. That's it. And we call that a pi pulse, because pi is 180 on the sphere. Well, what happens if I do a pi over 2 pulse? Well, I'm down the equator. And then I can allow this to process. And so now, how do I represent that in a numerical way? And that alpha and beta, think of it as angles on that sphere. You could say it's pi beta, whatever. But I can now look at any point on that sphere, and I can bring it down. And we'll demonstrate that. I've got some hands-on demonstrations here. We can play with later. I want to go pretty quick on this so we can get to those, because I think that'll be fun. And then there's another thing called entanglement, which is, if you thought superposition was weird, entanglement is even weirder, because I can take 2 bits and I can bring them close together. I can perform what's called a sequence operation on them, and then I can separate them at great distance, and I can measure an attribute on this one over here, and it will be exactly the same regardless if I separate that by the distance of the known universe. And it's these 2 things you combine together, the fact that I can represent numbers in a complex way. So now when I want to represent, I've got 3 bits. In a standard computer, 3 bits, I can represent a number 0, 1, 2, 3, 4, 5, 6, 7. In a quantum computer, I can represent all those numbers simultaneously. So when I do a computation, I'm not just doing a computation on one number, I'm doing a computation. I've set it up so that I've got some representation saying, well, I got a little bit of 1, I got a little bit of 2, I got a little bit of 3, a little bit of 0, and I got nothing of the rest. And then I'm going to do the computation on another number. And so here's part of the power. I'm now doing one operation and doing a whole bunch of numbers at the same time. And then what will happen, I'll demonstrate that here with just a laser, is you get interference between those. And then the interference produces your final number. And this entanglement now means that I can do that on many, many bits simultaneously. Do an operation on 1 bit, and it happens on all the bits. So I'll stop there for a moment, please.
Question. Compared to the chips that are in today's computers, how fast is quantum compared to like an Intel chip?
Good question. Very hard to answer, because so in an Intel chip, for instance, one that's in my laptop or something like that, they talk about flops, floating operations per second as a metric. But that, again, I just explained that we're doing all of the operations serially. So how do I then say I'm now going to do something where I'm doing many operations in parallel? So let's talk about something that's probably near and dear to Paul's heart, a fast Fourier transform. So the fast Fourier transform is actually what's happening right now on the screen here. I've got a laser, I've got a double slit diffraction grating, and I'm getting this nice pattern on this string here. And that's actually fast Fourier transform. Now, it's a really quick way of doing it. But if you did that on your laptop, that might take, I don't know, a few thousand clock cycles, something like that. So, and say your clock is a gigahertz. So I'm doing, so
But they might be a tenth of a
maybe it's a
second, but,
megahertz or something like that. That you can do, say a 32-bit FFT, something like that. As opposed to on a quantum computer, that's one operation. And if I say my gate speed is 20 nanoseconds, every 20 nanoseconds, I'm spitting out another FFT. That's a very specific case. We figured out how to do an FFT in a very highly parallelized implementation on a quantum computer. And so when you want to compare those two things, you actually want to take those particular cases. I'm sorry, again. I'm trying to make sure I talk your language. Please let me know if I'm not.
Okay, thank you.
If you know what a spectrum analyzer is, a Fourier transform is basically what the machine does. It looks at the spectrum of the signal. Anyway. Oh,
So-
more complex numbers.
Sorry. One of the things I'm trying to get across is that, as I said early on, this is a gateway drug, right? You always want to get, for me, it was, well, okay, that's not enough. What's the next layer? Okay, that's not enough. What's the next layer? And so on. So I am introducing you to something, and you're not going to get it. I don't expect you to get it in this brief time, but I'd like you to at least see it. So when I talk about, I've got a number A and I've got a number B, and I'm going to add 1 + 2, and that's going to equal 3. That's a fairly easy concept. You've had that in school. You've talked about it before. But here, we're talking about what's called a 2-level system. I can simultaneously represent a 0 and a 1. So how do I add those two things? And these are the types of operations that you can actually do. So you can see this. I did this with my arms. You can see this animation, this block sphere over here, where it's actually doing exactly what I did with my arms, where we got pi over 2 pulse, bringing it down the equator, and then recess. And then you're doing a 180 pulse. And one of the things this would be fun to do at some point, if you guys are up for some exercise, it's really unusual. So this is a weird concept. You can think of these as rotation matrices. So I've got my fist up in the air. I'm going to bring it down. I'm going to do a 90-degree. So I'm going to put this out to my side. I'm going to call that my x-axis. I'm going to do a 90-degree rotation around the x-axis. I come down to the equator. Now I'm going to do a Z rotation. Okay, so I end up there. Now I'm going to do the same operation. I'm going to do them in a different order. I'm going to do a 90-degree rotation in Z. And now I'm going to do an operation on X. And actually, I just end up in the same positions. That shouldn't work.
Yes, what
It's
you're
not
trying to
supposed to
do.
commute.
Oh,
That's what I'm trying to show.
oh. It doesn't commute?
It does not commute.
Okay, in general, you can't do it backwards.
You can't change the order in which you do things. I'm trying to figure out what I did wrong there. The rotation around
You just
X.
need more exercise.
Yeah, there you go. We should have run this through. I mean, I can do this. I can do rotation around Y. And I can. You end up in different places. Trust me, I did something wrong.
We'll try it again after, we'll try it again
We
after.
need a beer. That's
When we get to the fall, we'll figure this stuff out.
Yeah.
But suffice to say that instead of using plus and minus, things like that you learn in school, I had to learn all this new mathematics. And this is called, and I'm going to show you here, we've got these demonstrators, which you can play with later. This is called the Clifford group. And what that means is you're doing operations on a 2-state system, and they're non-commutative, and they don't change the magnitude. There's a whole lot of math. But the non-commutative is that, I can do this and then that, and I should not end up in the same position as if I did that first and then. Shouldn't.
Oh, I see.
And the fact that my arm always remains the same length, that's another kind of thing. So the only thing that's not.
I'll try that.
So the rays riding the surface of the sphere.
Yeah, that's exactly right. That's the thing you should really take out of this. You got it.
All right.
Okay, so now, again, I'm moving really fast. I apologize for that. So I've got a couple of things up here that I want to pass around. These, I've got demonstration of superconducting qubits. I'm going to pass these around. This is what's called a cavity qubit here. And that's a single qubit. And here's one that, if you look really carefully, you can kind of move around in the light and you'll see 3 qubits on it. And what they're made up of, I wish I had a pointer here. You can see that things being passed around is almost the identical thing to what's in that picture. And it's really just made up of, I'm going to move one slide ahead. It's made up of an inductor and a capacitor. That's it. And you guys should all know that. You built a crystal radio set?
Nobody builds radios anymore. Except for Willie.
Oh, come on.
Yeah.
You guys can build, that's what you should do. You can have a project where you come in and you build a crystal radio set. One of the funnest things ever. but it's just an inductor and a capacitor, then you can put a speaker on it. Cool, wow, cool. Yeah, we got that on there too. And what happens is,
When you were at the wireless museum, Nancy, when you were at the wireless museum, didn't they have this capacitor made out of glass plates?
They have lots of stuff
do.
there.
Oh, yeah, lots of stuff. Okay, all right.
well, if you think that, you know, New England Wires Museum, so you go upstairs and you see the spark gap transformer.
Right.
And you're gonna see big coils, those are your inductors, and the antenna plays into that. And then you see over here, if I've got the key right here, to your left, there's a stack of glass plates.
That's a capacitor.
That's your capacitor. That's your resonant circuit that sets the frequency of the transmitter. Same thing here. I make it a qubit, but it's a frequency of a transistor or transmitter. The only difference is there, you've got as much energy as you put in, you're going to get out. In the systems that are being passed around here, only single quantum of energy are exposed to. So I can sit there and now I can say, I'm going to have a 0, which is, you know, I don't have any energy in the system. A 1, I've got a little bit of energy. And a 2, I've got twice the amount of energy. I can't get anywhere in between.
And when you're doing multiple ins and outs, how you do the phasing?
How many people play with software-defined radio?
Mm.
Okay, so our entire stack. So when you say, like, suppose right now you were to download the
I was
software,
an
which
I'm
we
an
talk,
RF guy, so
Okay,
I'm
so-
dealing with phasing and.
you download this thing, and you're gonna program in Python, and you make a whole bunch of hits, where you make the problem, and then it goes down, and the last thing it is a rack of SDRs, and there's one per qubit. And you got I and Q, and so you're an RF guy. So think about that blocks. Have you ever talked about like symbol sets? How many people have played Ribbon? Or you know,
RTTY, yeah.
Whisper,
Yeah, whisper.
anything like that. So if you use any one of those things, what they're actually doing is they're creating an encoding. And what you're doing is, you know, like with radio teletype, you're just saying, I'm either up here or I'm down here. I got a 0 or a 1. And then there's QPSK. I'm going to hit all 4 quadrants. And then they get way more complex. I think Whisper gets very complex in how it does its encoding. And so you talk about this plane, and we would talk about the in-phase and quadrature components of that plane. And you can map out this whole, what they call a constellation. If we were to take that plane and fold it into a sphere, that's what you got, that block sphere. So that's how we do our rotations. And I love to make that analogy for people who have some signaling theory. Because as soon as you do that, you're bringing in a whole bunch of theory that's gone on for 50 years. It's very rich. So I lied to you a little bit. I didn't tell you.
Used to it.
Right. So if I just make a capacitor and inductor and out of superconductors, and I bring them down at a transition level, they will quantize, and you'll get the diagram on the my left hand side. Yeah, it's still your left. And what it means is that if I throw photons in, say, 5 gigahertz, I'm going to go from 0 to 1, 1 to 2, 2 to 3, and so on. Climb the ladder all the way up out of that well. So what we do is we introduce a non-linear device. Now, let me relate that to something that everybody's seen, a pendulum clock. So a pendulum clock, you try like hell to make what's called a harmonic oscillator. You want the thing on the left. That keeps the most accurate time. Typically, in the spring, there's a suspension spring. Well, also the pendulum itself is not quite right. So it won't end up being the perfect harmonic oscillator, and there'll be errors in this associated with it. And you'll get, over a period of time will either increase or decrease, and then you can try and modify it, but you're going to constantly be chasing the tail. So if you take apart some of the very sophisticated pendulum clocks, you'll see up there where they've got this spring, is it actually bends around what's called a hypercycloid. So it'll change the length of the pendulum as it swings. And so what you're doing is you're correcting for the thing on the right, which is called an anharmonic oscillator, and trying to make it on the left. And we like an anharmonic oscillator because what it means is if I send a 5 gigahertz photon in, that only goes from 0 to 1. Maybe it's 5.1 gigahertz that goes from 1 to 2, and so on. So I can actually uniquely address each one of those states. So I can now, I have a way of impressing a number on that system. Questions?
By the way, are you gonna get to the temperature that this is running at?
Yes, I'll get there.
Okay.
So, and I should probably speed up a little bit. The thing that got passed.
There's a
around-
test on this at the end, by the way.
I'm fooling around here. I'm trying to make an analogy. I got my crystal radio set on the right-hand side, and the left-hand side, I've got a single qubit coupled with a resonator. The resonator is just an LC circuit, and the qubit is another LC circuit. Make the two talk to each other. You know, think about it as two resonators. You have impedance matching. You're doing everything you do in amateur radio. You know, I want an antenna. I want to make sure my antenna properly matches my transmitter or my receiver, so I get the maximum amount of energy transferred between those systems. Same thing is happening on that left-hand side there. That's exactly what we do. We spend all of our time thinking about how you're going to do that. The difference is that we're talking about 1 or 2 photons, whereas you're talking about 10 to the 23rd or 10 to the 30th photons. I continue. Kind of talked about this, you know, I just answered that question, like you asked the question of how to control the phase. Very simple kind of schematic of saying you've got an arbitrary waveform generator, you have a carrier wave. This is actually, you guys will get this, it's carrier suppressed double sideband in your terminology.
By the way, there's a presentation that I did on called What IQ Can Do For You.
Yeah.
It's on the club website. So I've done it here, but I mean, you want to
And then
get a little bit more whimsical version of it.
and on the right-hand side, you see, you know, got our cryostat over there, and then a rack of electronics. That was our first gen of electronics, where when we first set up, we opened up this thing where you could log in as a person, anyone. You didn't have, you just create an account, didn't cost any money, and you could run jobs on a quantum computer. And it cost us, we were buying incredibly precise pieces of test equipment, and it cost $500,000 per qubit. A little on the pricey side. So we said, we had inside Watson, a whole group that is dedicated to doing RF type work. And he said to them, hey guys, you gotta bring the price down. They came up with this thing, which is a horrible name. We call it ICE, IBM Control Electronics. Very boring. I got to name the second generation though, and I'll tell you that in a moment. And that right there, that rack full of electronics is 27 qubits worth of electronics at about $25,000 a pop. So that's a significant savings.
I can take 2.
Hmm?
So I can get 2.
Too, sure.
And then just for fun,
Just
generation-
extra shipping
Okay.
for a small additional fee.
I love to tell this, is that I got to name the second generation of electronics. I called it Les Paul. How many people who know what Les Paul is? There you go.
Yeah.
And I already talked about this, because so, you know, you were talking about signaling, so you kind of pre-said it, but there's your chart saying what's your constellation look like and how do you get
You got a massive hybrid.
there. Yep.
Mhm.
That's it.
And all those little coax lines going down.
Well, that's what I'm saying, all those,
So-
coax, you gotta phase them and everything.
Of course, straight man here is asking why so. So we use, say, niobium as a superconducting metal, and niobium transitions at about 4 Kelvin. What's a Kelvin? Kelvin is a scale that was developed, and it's a kind of a theoretical scale. This goes back to Lord Kelvin, and they were thinking about, and these are philosophical discussions that require beer or alcohol of some sort.
Lots of beer now.
Right. And the question was raised, you know, what does it mean to have zero motion? When does that happen? At what temperature? And so that's defined as 0 Kelvin. And then they kind of project that forward. It's a linear scale, and it intercepts 0 degrees C or 32 F at 273.15 Kelvin. So typically, if you saw a bunch of people like myself talking in the hallway, we would say, we're living in a 300 Kelvin environment. And the transition temperature is very cold. It's below liquid helium. So we use liquefied helium And we use that, and that brings the superconductor down below its transition temperature. Question? Okay.
I was just saying, huh?
But, so here's another interesting fact. How many people are familiar with the two physicists out of Bell Labs, Penzias and,
Oh,
you know what I'm talking about, right?
the guys that did the Big Bang,
Yeah,
the
so
background radiation.
These guys down at Bell Labs, I think it was Homedale or someplace
Yeah,
like that.
yeah, Homedale, yeah.
Right, so they're trying to communicate with microwaves and trying to maximize, they got this noise. WTF, where is this noise coming from? And they find out as they move their big
Been in my
horn.
shack.
Yeah. Yeah, it was less than S9, I can tell you that.
And so they're moving this horn around the sky and they find out, wow, it depends on where you put it in the sky. And it turns out there is this background radiation that's 4.4 kelvins left over from the Big Bang Theory. So it's kind of this, we're getting constantly irradiated by this microwave radiation at 4.4 kelvin, which turns out to be about 10 gigahertz, roughly speaking.
Now, that's the temperature in space, pretty much, right?
Yeah, pretty much.
That's 4 Kelvin. 4.
Now, so the problem there is that
Keep that in
I
mind.
just told you that our qubits are at 5 gigahertz. So I'm giving this rule of thumb that 1 degree Kelvin is about 10 gigahertz. So if it sees this 1 degree Kelvin over 4 degrees Kelvin, which is 40 gigahertz radiation, it's white noise. It's kind of like, imagine me screaming at you at the top of my lungs. You're going to go crazy. So that's like the world is screaming at the qubit. So we cool it down, 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 so it doesn't spontaneously transition. We go down to 10 millikelvin, which is really cold. Now, it's not the coldest that man has done. It's really cold.
10 thousandths of a degree.
So you're cascading to get that somehow?
Yes. So the first thing you do is you use, anybody worked on it?
He's a refrigeration.
Okay, so your working fluid is what in your refrigerator tanks?
Well, right now they're using all kinds of, using isobutane now, some of them.
Okay, so take that away, take the isobutane away, use the same cycle, and I'm going to replace it with helium. The
Okay.
helium is your working fluid. And as soon as you get, the compression cycle is a little higher, you get 4 Kelvin at the other end.
Wow.
So you compress the living daylights out of it, pressure sits about like that.
Right.
Now, not huge in the grand scale of things. It's water cooled, compress the living daylights out of it, water cool it so it gets down to room temperature after we heat it up to 400 or 500 degrees, and then it goes over. And then the last thing you do, and if you were to go on YouTube, search for the sounds of IBM quantum or something like that. It's one of the most widely hit. Why? I don't know, but sounds of IBM. And you'll hear this. Last thing, it's a huge free expansion. So it goes from room temperature down to 4 Kelvin. So exactly how a refrigerator works.
Right.
Joule Thompson. And then, so that gets us to 4 Kelvin. How do we get down to 10 millikelvin? This is where it starts to get very strange. If you thought everything I've told you to date is strange, this is even stranger. This is another aspect of quantum. We actually mix helium-4, which is your standard isotope of helium that you would see like to fill up your balloons with helium-3 that comes from breeder reactors. And it's very sought after. It costs $75,000 for 20 liters. Very expensive. And you mix those two and you cool them to 4 Kelvin. And then you pull with a vacuum through this it's a weird kind of thing, through a kind of a resistance. And you'll separate the helium-3 and helium-4. And that brings you down to 10 millikelvin.
Wow.
And for those of you who want to really get geek out on physics, it has to do with the isospin of the particles.
What I'm hearing is you could fix my AC so I get cold today.
There you heard it.
What we needed is a little pipe to bring some of that cold down here.
Anybody can work. Fixing it's a little tough.
So this is a lab, one of the labs I built out there. This is using COTS equipment. This was meant as a promo.
The big white thing is over there.
Oh yeah, sorry. The big white things are the fridges.
Oh, so I 50K gets me 2 little boxes, but I still gotta buy the fridge to cool.
Oh, yeah. Ah, yeah.
But you know,
I understand the business model here.
Really fast.
I understand the business model now.
And then, this one is it's another promo video, and that's the CEO of IBM sitting with the VP of research in what we call the super fridge. Also, the interior name is GoldenEye because the guy who's working on it likes James Bond films. That is kind of 5 times the space of those little white things, and that reached the same temperature just 4 weeks ago. And we are the only company that has built that.
Oh. You don't put the guy in spite of it, huh?
No, maybe we'll find Disney and we'll get them even colder.
There you go, there you go.
So now I want to do some hands-on stuff. And so what I was going to try and do, all of these, obviously, it's very difficult to actually do a real quantum demonstration. It's really hard to get a single quantum. Actually, I would encourage you to come up and start to play with things or look at them closely. And I apologize to the people on Zoom. Maybe we can move the camera in closer. You can zoom in. What I've got here is a diode laser. Show that on the screen. And what you've got what's called double slit, Young's double slit experiment, or anybody? It happens that you get this interesting phenomena, and you guys will probably have to come up and see it. I don't know if it'll show up on the screen. Well, it goes from the dot. You actually get a pattern set.
You gotta see the pattern on the other side.
But come on up, come on.
No, no.
This is meant to be more fun.
Yeah, they're not gonna.
Go ahead, touch it. Now you actually can see it pretty well. If you look, so you've got a picture in the lower right hand side. In that picture, you can see the type of pattern you see on that index part. So what's happening? And what is really happening is that the classical demonstration of quantum phenomena. See that it actually will happen. You can go down to single photon. So they will put in filter, and statistically doing, say, a photon a second. And you'll see the same pattern. So know that this happens at the it's just 2 different patterns. We've got photon going through 2 sides, but 2 different patterns. We go back to the beginning of the presentation. I talked about how I introduce a phase, the alpha and beta. Well, that's exactly what we're doing. And the alpha and beta are those 2 different pathways.
I'm trying to get in front of it.
You want to swap it around? You do that. Speed left to right.
Yeah, go this way.
Oh, here we can do this.
Oh, there you go. Good.
Smart.
This could be part of the equipment you're operating.
That doesn't always happen.
No.
Okay.
And we can use a bunch of cops of regulation. Almost. There you go. You got it. Look at that.
No, it's okay. I'll move it over.
Go the other way. There you go.
So then what I've got here are polarizers. So that's a way of encoding. So I've now shown you, and by the way, if you guys are interested in actually get these things. So, we can turn these into kits and hand them out at some point.
Okay.
So now I'm going to take that away. So that's just it's a pass it around.
You were looking for a laser before? Pointer?
Yeah, I could use
Now, I see different slots here.
Yeah, there are many different rings, and then what you're doing is you're getting the 2 slits and you're changing the distance. Okay. And if you go ahead, put it back. I'll have you do the experiment of lining it up. We'll see that you get one pattern. Now let's go over to the next one. There's another one, and then the dots should start to
Get closer together. More than that.
Yep.
They're close together.
Yep.
Getting them in phase.
So now let me relate this back to amateur radio. It's because these are just like antennas. This is, so let's suppose you didn't have the antenna modeling software. You wanted to model the performance of your antenna. These would be the equivalent of a stacked yacht. Same thing. And you know, exactly same thing. All you're going to do is say, instead of a laser frequency, I've got 2 meters or I've got 170 centimeters, whatever it is. And you're going to get the exact same pattern. You just run the math.
Very tiny.
Right. Very tiny. Yeah. But I mean, so one of the things to think about is when I'm doing this, and I talked about this before, where that's actually doing a Fourier transform. This is the way when computers weren't the things they are today. You know, back in the days of vacuum tubes, you could do some pretty simple calculations, a lot of them, and they wanted to do complex calculations like this. They all made models. So this is an analog computer. In the instance.
Oh, I didn't show that. I didn't show the diffraction gradient.
Okay.
I think I'm out of focus because the autofocus isn't. We just back off the zoom. Oh, is the laser? Don't shine the laser.
Yeah, I joined the club last year.
This is the diffraction.
Really not been able to get to.
I appreciate it. So much like in-person meetings, so it's great to see you.
See the dot and the table? You should see the laser. You should see the laser. They can stop the laser.
Oh, we can all.
They can see that.
Okay. So then the next thing I want to do is I'm saying, okay, now I've showed you what's called phase intelligence. There's another way of thinking about it. I've got polarizers here. How many people have polarized sunglasses? Like, ooh, 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 ooh. So the cool thing about it is light coming off of here is unpolarized. But if it's reflected, it becomes polarized. That's why polarized sunglasses work so well. And these are little tiny Polaroids that I got at Amazon. And I can do, so like, I'm going to arbitrarily say that's horizontal polarization. And you can go and you can see that the dot passes through nicely. If I have the same polarization of both, the dot passes through nicely. So I'm going to say, when I was doing quantum key distribution, and I wanted to transmit information from one person to another, and I wanted to encode the information, the way I did it is I did it through polarization. So I can say, here, I'm a transmitter, and this, again, once again, relate that back to radio. So if you got your 2 meter rig, what polarization is that?
What I'm telling.
Depends on what I tell you.
No, but on the transmitter,
2.5 pounds for
vertical.
Well, you got a
It
hand.
would be the vertical or horizontal.
side.
Yeah, but it's going to be either vertical, well, it could be any one, it could be a certain, but typically on the repeater, it's going to be a vertically or
Oh,
polarized.
it is. The repeater is vertically polarized.
So your best way of actually picking that signal up, granted it gets randomized as it goes, it propagates through, but you want to do a vertical polarization, because you do some horizontal polarization, watch what happens. Nothing gets through. So now I'm going to pretend like that's my transmitter and this is my receiver. And I will introduce this nomenclature that's in the literature. Alice is sending me Bob a piece of information. Alice has got a horizontal polarization. Bob doesn't know what Alice is sending. He's going to check, oh, it works for horizontal, but it doesn't work for vertical. So that's my receiver. I check it by checking the encoding.
Do you have 3
I do.
polarizers? What somebody told me the other day was, if you put the 2 polarizers so that they cancel,
Yeah.
like you just did, right? There's nothing, right? And you take the 3rd polarizer and you turn it 45 degrees, some light will get through. But I think you have to do it from the beginning.
Yeah, but you're right. You gotta,
That's circular polarization. There's,
Yeah.
even though you
So-
don't see any light coming through, you can force
For
the
those
light
who are
into
really
45
interested-
degree and it'll go through the 2 polarizers, even though you couldn't see it before.
I brought in 2 copies of this.
I've been wanting to play that. I've been wanting
Here
to
you
do
go.
that since that time.
That is called quantum erasure.
Okay. Oh, what a cute tweet that.
So then I've also got these here that you can come up and play with. This is, I told you about qubits. And you can do a classical bit, which is either, like I read about, it's currently 0 state, flip it, and it's the 1 state. And then I've got a qubit.
I want everybody to get a chance to make one in the zero.
Come on.
I do that every day.
If you've done it before, it's okay, but then just make a 1 and a 0. Pass it on, and so you can make one and ask the next person what it is.
How do you make the one?
You flip it.
The red, whatever you want it to be, read the other one. So,
So here I've got what it's just like a. I was showing you the qubits. And so this one I'm projecting onto the X, Y, or Z plane, and this one happens to be in Y. By the way, these actually have a random number generator in it. So if you don't keep measuring it, so measuring always keeps it in the same state. And then I'm going to do a pi/2 rotation Y. I've still got a Y projection, but I've now got an X projection too. So you can start to fool around with that.
I'm lost.
You're always tough. So that, I just want people to play now, so I'm going to stop talking. Oh, and rockets and we've got enough time to play. You can actually do some demonstration. with this.
How do I talk to these qubits?
We're ready.
With radio. 5 gigahertz radio.
That's it. But what I'm saying, so in machine language, we can talk to bits.
Yeah, so what, we have this programming language, which is shareware, called Qiskit. I can send you the GitHub repository, and where you can do a pip. For those people who understand Python, you can do a pip install, and it's the whole thing, and start playing with it. And what we'll do is we have a free backend. You can connect to either a simulator or a real-time system.
So you basically shoot a radio at this thing.
Yeah.
And that'll put it in some state. Right? And then you shoot, and then off the back end is the other antenna where something comes out. You detect that with the receiver, and that tells you the
It's all
state. Well, for you it's Python. But what the machine's doing is it's just making a radio wave, goes down the coax all the way down to 10 millikelvin, goes shooting into here, right? Am I correct?
Yeah.
Right, and hits this circuit with this pulse of 5 gigahertz. And moves this qubit into one of these states, somewhere in the sea, right? And then, at the same time that you hit it, something comes out of it, which you can use the receiver for.
Well, no, actually, so,
All right, this is what's, I know
This
if I
is-
tried this, I did something wrong, but go ahead.
well, so you notice we had a resonator hanging off.
Yeah, okay,
Yeah,
that's
what
that little curly Q thing.
Yeah, so resonator for you guys is like make an antenna of a certain length. That's a resonator.
Yeah.
Yeah, it's a tuning stem. Exactly right. So in our case, we actually use it as a real tuning stem. Right. What we will do is we set that tuning stub at 7 or 8 gigahertz, and you will shoot a signal in and you'll look at the reflected signal. So actually, in this case, we want a reflected signal.
Oh,
And
okay.
you look at the phase of the reflected signal. When the phase of the reflected signal reflects the hybridized state of the qubit and the resonator.
That's simple to do.
Is that semiconductor material?
It is.
Yeah, yeah.
So this is an interesting thing. When I give tours inside of IBM, I like to, because they'll say like, why superconducting qubits? And you go, well, you don't realize. So IBM started doing silicon because they wanted to go from tubes to transistors, and you couldn't buy transistors in any kind of volume at the level of reliability in order to put it in a computer. So in the 60s, IBM got into the fab business. They were doing silicon transistors. And that was bipolar at the time, and then in the 70s, they switched over to CMOS. Parallel thing, they're always experimenting with what's a new way to do computing. In the 60s also, they started a whole project on superconducting switches. They were called cryotrons. And so IBM has contributed to room temperature, or not high temperature superconductivity, but has a long history of superconductivity. So I like to say this is where IBM had a lot of knowledge as how to manipulate silicon like crazy with how to make good superconductors.
So 12, maybe 14 years ago. It was at the high temperature superconductors, all the quantum communication experiments were being done. But now you're talking 4 millikelvin.
Yeah.
So what's changed? What changed?
Those high temperature superconductors are awfully noisy.
So it's strictly,
So if you did like a, say you wanted to do a high precision magnetometer, you could still do that out of a, like, for those people who did subsurface detection, that was very popular, having really high quality magnetometers that would go down to
The magnet trying to find a submarine.
kind of a,
you didn't hear that.
I didn't hear it. I didn't say it. I said it. You didn't say it.
It's okay for you to say it.
I can say it. Don't say it.
I can't agree with it.
it's kind of,
No.
the noise at that time was about a nanotesla per root hertz. And you could still get that with ITC superconductors. They're, for this, they're way too noisy. We haven't really made it, but if you ever go to, there's a conference on superconductivity, just like there is for everything. The big application that they're trying to do is metropolitan distribution of high power. So they have these ITC superconducting cables that in some, like going to a large city like New York City,
Yeah.
that makes a lot of sense. You have a lot of loss in New York City.
Well, the company up at Fort Devens was, they put in a kilometer of power distribution.
Have you been up to Devon's?
But the,
Not in about 12 years or so.
so you cut down the loss by
American
cooling the conductor.
Yeah.
But what about the cost of the cooling?
There is a crossover. Because once you get cold, I mean, so you spend a lot of energy getting cold. Once you get cold, it's almost nothing to maintain the cold.
Oh, really?
Yeah.
So you've got good insulation too, then?
Everything is going to be vacuum insulated. I don't know exactly how they made the superconducting cables. I know that the way they did it when I was at Fermilab, they did superconducting magnets. So you would have 4 Kelvin liquid state, vacuum, nitrogen jacket, or actually a return jacket of the gas coming off the system, vacuum, nitrogen jacket, vacuum. So you knock down the radiation coming in from the exterior. I don't know if they do anything that sophisticated. I mean, because essentially what you're talking about for the high TC, you can do everything at liquid nitrogen temperatures.
Right, because at the time they were, storm size.
Yeah.
Cryos was supposed to be, but that's not what you're doing anymore.
No, these are long
Storm
cables.
size right there.
No.
We've been ignoring our people on Zoom. Do they have questions?
Yeah, by the way, anybody got a question? You're on speakerphone.
I got a question.
Yeah, go ahead.
Chris, does this technology, in your opinion, can this be used for any medical applications? Or is IBM looking into that?
So funny you should ask that. So how have I been spending my summer and where am I going to be spending my fall? I'm actually installing one of these at Cleveland Clinic. And the specific interest there is to work, so it's IBM research working with Cleveland Clinic on what sort of medical applications can be adapted to a quantum computer. And I think that what it'll end up being is largely on drug discovery, probably focused predominantly on cancer therapies.
Mhm.
But
Thank you.
in terms of where we have spent a lot of money and time, the 2 big ones had a lot of success on battery technology. We're not quite there where we can really advance it, but there's a lot of places where, because you want to get high density energy in batteries. And then I always say it's one step away to think about corrosion. And we made a lot of progress on corrosion, which is of interest to almost everyone. I mean, if you're the Navy, I mean, I think the first thing that happens is as soon as you leave the shipyard, the needle guns come.
What will
Been
sailors
there,
do?
done that.
What will sailors do with corrosion?
Been there, done that.
Anytime I've ever been
I
on,
sat hang over the side in the bosun's chair.
bang, 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 bang. And no matter if you have a bunk like anywhere in the ship, that's all you hear. I'd help you if you're sleeping during the
And
night.
I have one more question, just because I missed it, because the sound wasn't translating to Zoom. What did you say about 60 years away?
Oh, what I'm thinking, this is a dream of mine, which is that if you look kind of at how classical compute is today, we've hit the barrier for scaling. So certainly in the last 20 years, new computers have come out, and I think when I was in grad school, they were kind of 120 nanometers or so for feature size in a typical processor. And you can say, how many transistors? I mean, like Intel is always fond of advertising they're at 1 billion plus transistors. That has to do with the scaling and size of the transistor. The latest we've gotten to, IBM demonstrated, but this is in the lab, 2 nanometer scale transistors. But that costs, and somebody was raising like, where's the crossover in terms of the equipment cost? It's on the order of $2 billion to do the lithography for that, for the lithography tool to get to 2 nanometers. So that's diminishing returns. So that at some point, this kind of binge we've had for the last 20 years for classical compute scaling up and getting more and more powerful is petering out. So what's next? And my opinion, and that's why I'm invested in it heavily, is quantum computing is the what next. You're going to combine it with classical compute. You're going to be able to give another 60 years to computation, and it's going to be a deep level research. I mean, you think about it, semiconductor research has been going on. The first transistor was 1948, I think.
Predates, it's about that.
About that time.
Shocking,
So
but,
you think about that one that you see on the web. And so we've had a really good run with that technology. It's time, we need something new to bring us forward. So I think that if this all works out, one of the big problems is that almost everything we use is really odd. And we have really severe, you think supply chain problems just due to COVID. If I'm saying I want, one of my favorites is to talk about these very low noise amplifiers. We buy them from one vendor, and I think that vendor employs 9 people. That is not a good position to be in. So what we're trying to do, and that's actually, I think it's in Finland or Denmark or someplace like that. You want to get other places to get involved, so you have other vendors. So we're trying to figure out how you scale that out.
There's an RF amplifier.
Yes. Broadband, because it's hard to get. You got it. Obviously, you figured this out, that it's your bandwidth product.
But one of the things that is that there's this thinking that quantum computers is just going to replace regular computers,
No,
and that's
not
not the
gonna
case at all. So, I mean, basically, you have a regular computer interpreting the results from a quantum computer, or gives a job to a quantum computer to do that it can do well, and then takes the data back and analyzes it the way it typically do it. So it's not like this going to be just people doing quantum computers and people doing regular computers. They interact by giving jobs one to the other that they're better at.
So what I'm going to do by analogy, if you look at the high performance supercomputing centers around the world, IBM has put one in Oak Ridge and Lawrence Livermore. I can talk to those. There's ones at Argonne. There's one in Maui, which I would love to get a system installed there. But what they are they're Intel processors combined with NVIDIA GPUs and also FPGAs. So you'll get, I don't know, Xilinx or somebody like that. So you've got all of these, and then your operating system becomes very complex because you're going to shoot this problem, and it's going to go say, and this gets really hairy, especially when you have an FPGA, because you may say, all right,
FPGA.
Oh, yeah.
Floating,
Field programmable gate array.
Field.
It's a piece, it's a circuit that you can program to be whatever you want.
and you will make it so it's ultra high speed at maybe one specific operation. And you kind of have to tell your operating system, go over there if you want to do this one operation. So we have this huge intractable problem, and the operating system will say, okay, this part goes over to the GPU, this part goes to the FPGA, this part goes to the classical processor, and now we're saying, oh yeah, we're going to add quantum processors in here too. So it'll get fanned out depending on what is the best piece to solve the problem.
Chris, I I've lost my audio, and in the very beginning, you had a very interesting looking golden chandelier. Maybe you explained what it was, but I did not hear what it was.
It's a refrigerator, but he's gonna show you. Hold on.
So it's a mock-up. It's an advertising tool that we use to, and if you ever came to visit me, this would be one of the first places I'd take you. It's stands about this tall, and it's in a roll-around rack. About, I'm going to say, a yard in diameter. And it shows all of the cooling technology that I described in words here. The pulse tube, which goes from room temperature down to 4 Kelvin. And then what's called the still, where you're separating the helium-3 and helium-4 in the center. Can't see either of those on this photograph, but you see each one of those wires that all represent coax. Oh yeah, there you go.
I knew this laser would come in handy for something.
So you got the coaxial wires there. You can see that if you go up to the upper left there, that's the end of the pulse tube, I think. This thing, oh, up there, right there.
Yeah, it's not coming through.
Oh, the red's not coming through?
No, sir.
Okay, anyway, and what you've got in there are a whole bunch of, you've got circulators, you've got filters, attenuators, they're all very common passive RF components.
Chris, is this a schematic of something that exists, or is this an actual operating device?
It's a schematic of something that exists.
It does look like this, doesn't it?
It looks like this, but I will be very frank with you. We don't ever want to actually show exactly what we do. People reverse engineer it. So this.
What kind of people would do that?
No one here speaks Mandarin. What are you worried about?
At least you got the right country.
Hey, tell them about the little circle.
Oh, so that's interesting. That's a good point you bring up. So I said this cools down to some exquisite temperatures. And one of the problems is you've got what we call CTE mismatch. And what does that mean to the average layman? And what it means is that, and you guys have seen this, you've seen where things contract very badly at low temperatures. Those loops are essentially springs in the coaxial cable, so that as it cools and the overall size of the apparatus shrinks, that will just absorb that distance change. And then when it warms up, it just relaxes. Otherwise, go ahead.
Is that any special kind of gold?
No, it's actually fairly common gold. So let me give you my spiel on why gold. There's a bunch of reasons. The first reason is that it doesn't oxidize, which is really nice. And then the second reason is that the temperatures we're talking about, you've got 3 mechanisms in which to heat up the inside of the cryostat. The first thing is convection. So you've got an oven. And so the first thing you do is you evacuate that space. You put it into a pretty vacuum. So you take away the convection of that. The next problem is conduction. And so we use stainless steel to support this. And if you don't believe it, stainless steel is the worst thermal conductor you could possibly be. Great for us, very strong, very poor thermal conductor. The last thing that you wouldn't really think about too much, what's called black body radiation. In each stage, so if I'm looking at the 10 millikelvin stage at the bottom, and then above it is 100 millikelvin.
The
So
market.
it's like, imagine that I've got the
The
sun.
bigger one.
No, I got you.
Oh, down on intermediate
I
stage.
know, but I did.
So somebody want to
Hey,
mute their
Don,
microphone?
Tanya, your mic's hot.
So what you do is for each stage, you actually put a cylinder around it, and that's gold plated as well. And you can think of the gold as a mirror. It's a mirrored surface. In fact, if you ever look anything out of NASA, it's very fine mylar that's gold plated. And that's whole purpose is so that you reflect the sunlight and it doesn't get that hot on the object they're trying to protect. It's on all of the telescopes, all of the satellites and everything. The last thing is that at these temperatures, it's really hard to make thermal contact between 2 pieces. So when we mount our qubits or anything else that we want to actually thermalize at those temperatures, it's only a point contact unless you've got gold to gold. You put gold to gold, You slam down on those torque wrenches and you basically make a cold well. You got really high quality thermal contact. So I just gave you 3 reasons why gold.
We should probably let people get going to work. It's almost 9 o'clock.
That is-
Any other questions from the remote audience?
Yeah, there was one that was asked by Eric in the chat channel, and he says, how much does quantum computing rely on the spooky action at a distance phenomenon? I think he means probably entanglement.
Yes.
He
yes,
says,
that
is
is
that
a-
completely unrelated phenomenon? He says,
Not at all.
sci-fi has confused me.
So you see this, what I've got on this slide here, you got 0, 0 plus 1, 1 over √2, and the √2 is a normalization factor.
Yeah.
But what you're saying, this is what I was describing, that is the spooky action at a distance, that I can entangle these 2 qubits using a C0 operation, and then I can separate them to any distance I like. And when I measure the property of one, if it's a 1, it will be, I know it's going to be a 1 at the other. So when I'm actually, there's this phenomena which we call teleportation. Okay, it's not the Star Trek teleportation.
Close.
But so I will take and I will do a C0 operation. And I take one of the bits and I may move it all the way to the other side of the computer. And then I do an operation. So that distance, and I'm just for those people who do computer science, rule of thumb is that it's about a nanosecond per foot, roughly speaking.
It's light
Plus
speed. Yeah, nanosecond per foot.
roughly speaking. And so if I want to do, if I'm making a classical computer and I actually want to have a clock talk between the 2, this is like a huge problem in big classical computers, that I actually have to synchronize these 2 really, really closely. And that is a non-trivial thing. Many people spend their entire lives figuring out how to do clock tree distribution. In a quantum computer, I can separate those and I can perform an operation on this bit, and it happens over here at the same time. And I don't have to worry about the fact that they're not synchronized. So that's that spooky action at the distance. Now, just as a one thing, because I'm going to like predict there's a follow-up thing. Does that mean I have faster than light propagation? No, it does not. Because you require a classical channel to actually say that actually happened.
What if you had perfect resonance?
Perfect what? Resonance? So good observation on your part. I will tell you, no, that's actually a really good question because.
Yeah, it sure is. I don't even understand the question. It's really.
Well, no,
good.
so I may be reading more into it, but there's a part of this. We actually talk about the quality factor in all this, like, okay, standard radio, like if you picked up a AM radio that you bought out of a supermarket or something, the quality factor in that resonance circuit at best is going to be 100. When I've made my crystal radio sets, I work really, really, really hard to get a Q factor of 100. In these, our Q factor is about 10 million to 100 million. So very high Q, and there's 2 things that are going on there. That means that it has a very narrow, what we call line width. That means that the frequency is extremely precise. So that when I address it, I'm addressing it down. So if it's 5 gigahertz and I've got a 10 million Q, you're within a megahertz or so. So even actually less than that, kilohertz.
Yeah, probably, yeah.
So
It's like
that's very tight.
5,225,325. About 10.
It's very tight in terms of that. And then what also means is that I'm less likely to lose energy from that circuit. What I didn't talk about, and you can see that I could endlessly talk about this stuff. I didn't talk about the resistance in the circuits. So the resistance is extraordinarily low. That's your dissipative nature. And then there's this other thing, which we call decoherence, where you can spontaneously lose energy to other parts of the circuit. Another topic for another time, but the whole quality factor is how we measure all of those properties.
So the highly resonant circuits, I guess, is.
Yeah.
Is that what you wanted to know?
Well, he said the entanglement is any distance. So theoretically, then that could be a distance such that to entangle would exceed the speed of light.
That's a very complex topic, actually, but.
Let's get together and we'll have a whole session on that.
In theory, I guess in theory, things happen at a distance simultaneously without the speed of light, but you can't tell that they happen unless you use the speed of light to find it out.
That is correct.
So,
Oh, I see.
so you
That-
can't beat the speed of light in terms of information. Even if the thing was switching instantaneously, you could never tell. Because you need this, because the only way you could measure it was to get something from here to here, and that can only happen, it can't happen any faster than the speed of light.
Right.
That's the way I understand it anyway.
You understand.
What I have to say is that we're incredibly lucky to have you as a local resource, and it was super great for you to see, for you all now to meet Chris and see how enthused he is and able to. And he actually comes to breakfast sometimes at Chelsea, so you can actually just nerd out even more about all this. You know, a lot of people have to.
By the way, one thing I tell you about Chris is he loves to do crystal radios. So if you don't want to do a quantum computer in your house and you want to build a crystal radio, he's also your guy. So, yeah, he's an expert at you know, very.
Let's get a big,
Oh, I was, guys, just one last question when you mentioned crystal radios, because there's another, I wanted your opinion on them. Ex-IBM research guy that puts out a lot of YouTube videos, Dan Winter. What do you think of him?
I'm not sure I know Dan Winter. I'll have to look him up.
Yeah, he has. No, he has a website, but I don't have it handy.
We're gonna pick the raffle thing before, you ready? Who wants to pick it out? How about Linda or Chris?
I bought.
Yeah, I know, but
Tickets.
you can pick because they're random.
I don't know. I ran it up.
See, I'm watching the spooky action at a distance on my.
I'm assuming it's last three digits, 378.
795378.
3, 7.
Somebody's got it.
378.
3.
Always gotta have it.
8. Get out of here.
7, 8, on.
Oh, there we go.
All right, Mark. All right, way to go. Yeah.
Anyhow, Chris, thank you so much. And, you know, it's incredible to have this kind of expertise in the club also. And I really appreciate your starting off the radio part then too. So please feel free to chat with them. But those of you that have to get paid, you know, to work in the morning, I know that you get up at 5 o'clock. So
Bob, you want to stop the recording, please?
Okay, yeah, let's see.
yeah, so, part one. Okay.
Is there anybody on the Zoom